Hello everyone, myself Dr. Sridhar, Assistant Professor of Mathematics, Government First Grade College, Gokak. So today I am taking the topic rings and fields, which is a prescribed syllabus by the Rani Chennamma University, Belagavi. So let us start. Okay, so rings and fields. So a ring is defined as it is an algebraic structure. So algebraic structure means what? So algebraic structure means it is a set which satisfies certain laws. Okay, it's called as an algebraic structure. So here in a mathematical way, a ring is defined as let R be a non-empty set with two binary operations, addition and multiplication. Then R is called a ring if it satisfies the following laws. Okay, so the first law, laws of addition. So under this, again there are sub laws. So first one, for all AB belongs to R, A plus B is equal to B plus A. Next, second law is A plus B plus C is equal to A plus of B plus C for all A, B, C belongs to R. Next, third one, there exists an element 0 belongs to R such that A plus 0 is equal to A for all A belongs to R. So then 0 is called as 0 element of the ring. Next, fourth law, for all A belongs to R, there exists an element minus A such that A plus of minus A is equal to 0. In that case, minus A is called as negative element of A or the inverse of A Next comes the second one, second main law, that is law of multiplication. So in that, A dot B dot C is equal to A dot of B dot C for all ABC belongs to R. Next comes third one, distributive laws. So it states that for all A, B, C belongs to R, A dot of B plus C is equal to A dot B plus A dot C, and B plus C dot A is equal to B dot A plus C dot A. Okay, so if any set R with two binary operations, addition and multiplication, if it satisfies all these laws, that is laws of addition, under laws of addition it should satisfy all these four laws, and again under laws of multiplication it should satisfy this law, and it should also satisfy these two distributive law. So this is called as a left distributive law and this is called as a right distributive law. So if a non-empty set satisfies all these laws, then it is called as a ring. Okay, so now if suppose that there exists an element 1 in R such that 1 into A is equal to A into 1 is equal to A. In that, for all A belongs to R, then 1 is called a unit element, and the ring R is called as ring with unity. R is called as ring with unity. Suppose that if there exists an element 1, if you multiply a number which belongs to R with 1, then it should give the same number. So then 1 is called as the unit element and the ring is called as a ring with unity. Similarly, a ring R is said to be a commutative ring. If AB is equal to BA for all AB belongs to R. Okay, so now we take certain examples on this. For example, say a set of integers. For example, set of integers. Say S is equal to. So under integers 0, 1, 2, 3 and so on. Okay. Now consider this set of integers. Now this set of integers, clearly it satisfies all the laws. That is law of addition. Law of addition. So if you take any two numbers, say 2 and 3, if you add either 2 plus 3 or 3 plus 2, then it gives the same answer. 2 plus 3 is equal to 3 plus 2. It gives the same answer, that is 5. Similarly, the second law also it satisfies the second law. A plus of B plus C is equal to A plus B plus C. Okay. So clearly and similarly, it also satisfies the law of multiplication. Okay. And it also satisfies the distributive law. So therefore, it is a ring. And one more thing here, observe that there exists an element 1. If there exists an element 1 such that 1 into 2 is equal to 2 into 1 gives 2. So that is called as 1 is called as a unit element. Say there exists 1 belongs to this set of integers such that, take any element 2. 2 into 1 is equal to 1 into 2. It gives the same number 2, again which belongs to the set yes. So therefore here 1 is the unit element. So the set of integers has a unit element, that is 1. So therefore this set of integers is also called as a ring with unity. Therefore set of integers is a ring with unity. Okay. Now similarly, if you consider the set of even integers, for example, take the set of even integers, say 2, 4, 6, 8, 10 and so on, only even integers. Okay, so now here it is a ring because it satisfies all the law of addition and all the rules in that law of addition, and also it satisfies law of multiplication. It also satisfies distributive law. So but what happened here, there does not exist a number such that when you multiply that number with any of these numbers, it should give the same number. So that is there does not exist an element 1 such that 2 into 1 is equal to, or 1 into 2, it should give the same number, that is 2, because 1 does not belongs to this set yes. So 1 does not belongs to this set yes. So therefore there does not exist any unit element. So therefore yes is a ring. Without unity. S is a ring without unity. Okay, because take one example. So 1 into 2 it gives 2, or 1 into 4, 4 into 1 it gives the same number 4. But 1 does not belong to the set of even integers. So 1 is an odd number. So 1 does not belong to the set of even integer. So it does not have any unit element. So therefore yes is a ring without a unit element. And therefore yes is not a ring with unit. Therefore yes is not a ring with unity. Okay. And similarly, the set of all real numbers, the set of all rational numbers, and the set of all complex numbers, all are a ring with unity. Okay. So this is about a ring. So now we prove its properties. Now properties of a ring. Now properties of a ring. So it states that first property, that is, if R is a ring with 0, if R is a ring with 0, then for all AB belongs to R, for all AB belongs to R, A dot 0 is equal to 0 dot A is equal to 0, is equal to 0. Okay, is equal to 0. And second one is A into minus B is equal to minus A into B is equal to minus of AB. And third one minus A into minus B is equal to AB, is equal to AB. Now see here, before proving this theorem, I want to tell you one more thing, that if there exists in a ring, if in a ring, okay, in a ring, if there exists an element 0 belongs to R, such that 0 plus A is equal to A for all A belongs to R, then 0 is called zero element of ring R, 0 element of the ring R. Okay, now similarly, in a ring R, if there exists an element minus A, such that A plus of minus A gives 0 for all A belongs to R, okay, for all A belongs to R, then minus A is called inverse of A, inverse of A. Since here the operation we use here addition, so it is called as additive inverse. If the operation is multiplication, then it is called as multiplicative inverse. Okay, so these things we should remember. So next we prove the theorem. So proof. So first, to prove the first one, just now I have told that if there exists an element 0 such that A plus 0 is equal to A. Okay, so now it is given that R is a ring with 0, that means 0 is the element of the ring R. Okay, so now therefore according to the that is 0 element property, so A into 0 plus 0 gives A into 0. That is, it is similar to that of this. Consider this whole as A plus 0 is equal to A plus 0 is equal to A. Okay, now this is equal to A into, again 0 can be written as 0 plus 0. Again this by distributive property, A into 0 plus A into 0 plus A into 0. Okay, so now here consider this one and this one. Here one A into 0 and one A into 0 get cancelled, so which implies A into 0 is equal to 0. A into 0 is equal to 0. So this we prove. Similarly, to prove 0 into A is equal to 0, again we apply the same property. So now consider 0 into A plus 0 is equal to 0 into A, again by the properties of 0 element, is equal to, now this can be written as 0 plus 0 into A. Again this is 0 into A plus 0 into A. Again from this one and this one, 0 into a, 0 into a, so this will cancel each other. So which implies 0 into a is again equal to 0. So this is call this equation as 1 and this equation as 2. So from 192, from 192, a into 0 is equal to 0 into a is equal to 0. So this is the proof of first one. Next we prove the second one. Okay. So now take the second one. So here what we do, consider second one. Consider a into minus b, then bring this here plus ab is equal to. Now in this case I take a common. So if I take a common, then minus b plus b is left in bracket. This is a into 0, or just now we proved a into 0 is equal to 0. So this is 0. That is a into minus b plus ab is equal to 0, or this implies minus ab. Minus ab is the inverse of a into minus ab, or we can write a into minus ab is equal to minus of ab, Okay. Now similarly we prove minus a into b is equal to minus of ab. For that we consider minus a into b, then again same plus ab. Now in this case we take b common. So in bracket what we get, minus a plus a into b, which is equal to minus a into plus a gives 0, that is 0 into b. Again in the first one we proved that 0 into a is equal to 0, so this is equal to 0. So from this equation it implies that minus of ab is inverse of minus of ab. So this implies that minus a into b is equal to minus ab. So therefore from this equation, from these two equations, call this equation as 1 and this is equation 2. So from 192 a into minus b is equal to minus a into b is equal to minus of ab. So this is the second one. Next we prove the third one. To prove the third one, consider minus a into minus b is equal to. Now using the second property, this can be written as minus of a into minus b. Okay, this can be written as, take minus then a into minus of b, or this is same as, now what is a into minus b according to this property? Minus ab. So it is minus ab. So this implies, now minus ab is nothing but what? Inverse of ab. So minus ab is inverse of ab. So therefore this can be written as minus a into minus b is equal to minus of ab, because minus ab is nothing but inverse of ab. So inverse of ab is, that is ab, or again it gives, this is equal to minus becomes plus, this is equal to ab. Minus becomes plus, that is equal to ab. So this is the third one. Okay, so thus we prove the properties of a ring. So the first property is a into 0 is equal to 0 into a is equal to 0. Next, a into minus b is equal to minus a into b is equal to minus ab. Okay, and then minus a into minus b is equal to a into b, a into b. Okay, so in the next class, we take some more theorems on this. Thank you.